Hi, my students. It's good to see you. I wish we could see each other face to face, but I've been playing with this technology and I'm hoping that this is a pretty effective way for me to get to teach you through the computer. So you have this shared with you because you've already finished your water cycle web quest, and I wanted to be able to teach you through it and emphasize the same things that I would have if we were in class together. And so let's go ahead and go through the 8 main water cycle words that I wanted you to master through this. So first of all, I come over here and we highlight evaporation. And you notice with the evaporation, we're seeing the water actually going up. And so there's a science reason for that. And here comes the science reason. It's really in this diagram here. So we can see that the water molecules start to spread further apart. And so when you have squishy mass, we call that high density. But when the mass gets spread out like this, it's lower density. And lower density things will rise up. So the definition you should have is that evaporation is always a liquid to a gas. And I guess that's the whole point in the water cycle. It's always chemically H2O, 2 hydrogens bonded to 1 oxygen, but we're always changing states of matter through the water cycle. And of course, evaporation requires heating for it to happen, for the molecules to get further apart. Now, the key question to answer about evaporation there was, what is water vapor in the air called? And we actually call that a weather word, humidity. And think about this: what season do we tend to have higher humidity? And I accidentally gave that one away. It's generally summer, which makes sense because in hotter weather we have higher evaporation rates. So again, evaporation is liquid to a gas. Now, I come over here and we look for condensation. Now you'll see condensation is way up here in the sky, right where the clouds are forming, which is a really important thing to note. And condensation is very much the opposite of evaporation. So let's think that through. So evaporation goes liquid to a gas. Now finish my thought. That means that condensation must go gas back to a liquid. Now let's flip this. If evaporation requires heating, that means condensation then must require cooling. And so if you check out my definition, I've got that condensation is gas to a liquid and requires or needs cooling. And then this is a super important question, actually. The concept of, are clouds made directly from evaporation or condensation? Through my time teaching, I will ask students, what forms clouds? And they'll almost always say evaporation. And like they're onto something. Evaporation is needed for cloud formation, but it is only the first step. So as I highlight over here, this first section is showing evaporation. You can see it says rising water vapor. Now, this business of particulate matter is a fancy way basically to say volcanic ash. There's ancient volcanic ash, little tiny bits in our atmosphere, and that actually gives the water something to condense around. And so here is actually cloud formation. So as you go higher in the atmosphere, the temperature gets colder. And physically what the molecules do, remember it's a vapor after evaporation, so they're spread out and squirming around. Now the water molecules start to pack together as they get colder, condense together, and eventually it'll go from a gas all the way to a liquid. And so I think that clouds look like a vapor, but they're not. And if you think about it, what comes out of them? Well, rain, snow, sleet, hail. It doesn't precipitate a vapor down on us. So it makes sense that they would not be vapor. So clouds definitely form directly from condensation. Evaporation is first, but then it's followed by condensation. Alrighty, so continuing on now, we have our next water cycle word, and it is precipitation. So you can see right there some happy little water drops leaving the cloud. And this is probably a pretty familiar water cycle word to you. But the interesting question that goes with it is, what is precipitation like? If we think of the atmosphere like this super highway that moves water around, we have precipitation kind of like the exit ramp. So it's really important because it's returning water back to Earth's surface so that it can be evaporated again and condensed again. Now, precipitation is just falling water from clouds. And this is kind of an interesting diagram that shows the difference. The idea that in higher up clouds, a lot of times it's actually frozen water. It might start as snow, but then fall as rain. And it also shows us here the difference between freezing rain, sleet, and snow. And all of these would be different forms of precipitation. Okay, now our next one is runoff. So you'll notice these look like some of the happiest water drops on the whole website. They're having a good old time. And so runoff, you can see that they're heading downhill into oceans in some cases, into groundwater in some cases. But runoff is really what it sounds like, that the water drops are running downhill due to gravity. And so I like this picture, because you look and you're like, well, I don't see much gradient there. You might remember that word meaning slope, but there always is a little bit, and you can see that running down an agricultural field there. Okay, so the force of gravity is the important thing there. Now, how does runoff actually recharge the groundwater, though? And that's what most of us drink is well water. Well, the idea that when we see it running off after a storm, the truth of the matter is some of that is soaking in. It's not all just running off into a river or ocean or lake. Okay, now our next one is a spring. And I bet some of you have springs on your property. And so when we look at the spring on the website, you can see this one looks like a happy little water drop too, just kind of coming out of the ground there. Well, what's really going on science-wise when we have a spring? It's when groundwater meets an opening at the surface. So let's look at this picture from nature. So you can see kind of a V-shaped valley there. So probably there was a river once upon a time, but we don't see one now. But it almost looks like it. And you see this spring. Well, where's the water flowing from? It would be flowing underground downhill. Now, this is kind of tough. But what this is showing you is this exact situation, but you have to kind of rotate that picture towards you. And so you can see it uses this word impervious and impervious. Another way to say that is, or a way to define it, this impervious layer would be something tightly packed that water doesn't get stored or run through. This pervious layer would be more like a sandstone where water can come through. And so you'll notice that underground here, there must be a layer, kind of like a sandstone layer, where water can flow and it's meeting and opening at the surface. So spring water is truly a type of groundwater. I hope that made sense about rotating that, and you can see the geology, the rock layers underneath, and how that would make the spring. Okay, so we just have a couple more now, and we're getting to some words that probably are not quite as familiar, like evaporation, condensation, precipitation. They're usually familiar to students. Many of us have heard of a spring. You can make inferences about what runoff will be, but infiltration is a little bit tougher. And the word isn't directly on here, but on the site you used, it was right about here. And so I always equate this or think of it kind of like military battles. So when you're learning about the Civil War, if we say the Union Army infiltrated the Confederate lines, it means that they actually got into the Confederate lines. So when water infiltrates the soil, it means that it's just soaking into the ground. So infiltration is super important to us that depend on groundwater, well water, because it's actually the process where the water soaks down in. Now, this is another interesting little thing right here. So could our groundwater in Ohio actually be recharged, which means refilled, if it rained somewhere else? And the answer is yes, because the water can flow sideways underground. Now, sometimes this wouldn't be the case. It would fall directly, and then it would refill the wells, the groundwater right there. But sometimes it can actually move sideways if it's the right type of rock. And that leads us nicely to this next term. Now, this is a term that sometimes students struggle to pronounce right. The way that you say it is aquifer. And aquifer is not directly noted on here. But it did say groundwater storage. Now, here's the weird thing. An aquifer is not water. An aquifer is a rock type that holds water, and not all rocks have the ability to do that because they don't have a lot of pore space or hole space in it. So if you check this out with me, notice I'm highlighting the word rock. Aquifer is a rock under the soil that stores water. And then the critical thinking questions there, the key question, Why don't we have groundwater too deep in the crust? Well, the first reason is the rocks get too dense down there, too tightly packed, and so the water wouldn't be able to stay. But this, I think, is the most important one. It's getting too hot down there for the water to stay a liquid. Finish my thought. That liquid would actually turn to a gas. It would turn to steam. So you don't have aquifers, rocks holding water, as far deep down as you would have rocks holding oil or gas, for example. And so I wanted you guys and girls to check out this with me, though. So this map is a U.S. aquifer map. Now, what do I mean by that? So get this, think this through. Are aquifers water or are aquifers rocks? And the right answer to that is rocks. So these are all different, the colors are all different types of rocks around our country that have the ability to hold water. Now you'll notice way up here in New England and Maine, they don't have a lot of rocks that hold water, which means that they would not be able to depend on well water. Their rocks up there are mostly igneous and from cooled magma deep underground, and they do not have a lot of hole space in it. But you'll notice most of our country, Ohio included, like look right here, it's no shock that we can depend on groundwater. We have very good rocks here for the ability to hold the water underground, and most of the country does. Now here's the catch though. When we've been studying the California drought, we can see that they have some good rocks to hold water. That does not mean that there's always water in there. You can obviously take the water out of the ground faster than nature can replace it at times. So it doesn't mean that the rocks always have water in them, but it means they're capable of holding it. And so we're pretty blessed as a country to have lots of spots where we could use groundwater as a resource. Okay, and then the final one is a T word. And so I know that the little runoff molecules are looking super happy. I think these two look like they might be falling in love. Okay, so those water drops are having a picnic, but I fear that their love story is not going to have a happy ending because you actually clicked on evapotranspiration there, which gives us a hint of what's happening. Water is actually held in plant leaves. And so the water within the leaf actually can evaporate out, and we call that transpiration. So you know that this has been happening when you see a leaf that looks wilty, like if you have hanging baskets. We have hanging baskets at home in the summer. I know they need watered because the leaves will start to wilt, and that means that transpiration is happening faster than the water can suck up the root, suck up through the roots. So how do we want to define it? It is just evaporation from plant leaves. Now, I hope that you actually clicked on this and got to see the close-up of what was happening. So this is a bag around a section of leaves on a tree. And so it is showing evidence that two things have happened. First of all, evaporation had to happen from those leaves because you can see liquid water drops. Now, be careful. The liquid water drops in there are not from evaporation. A gas going back to a liquid is condensation. So there's been transpiration, evaporation from leaves, followed by condensation. And this is very much like cloud formation. Now, just a little extra, something that you might be curious about. So this is a picture of the underside of a leaf. And so it's not like we could look at the underside of a leaf and see this. This is a microscope view. So you'll notice these little holes here. Those are actually called stomata, and the cells on either side are called guard cells. And plants have processes where these cells will inflate or contract on either side of the hole called the stomata, and it allows for gas exchange. So normally, we're talking carbon dioxide in for photosynthesis, oxygen out after photosynthesis, but also water vapor can leave. And if you think about it, the leaf would explode if this wasn't possible because you'd have all that pressure of the evaporating water. It needs a way to get out. So I hope that this was helpful. I'm trying my best. So please don't hesitate to email, to text, to give me a call if there's anything you have a question about. Again, my phone number is 740-644-2221. And we're doing our best. We're doing our best with this unprecedented time. So I care about all of you, and I miss seeing you face to face.